I would like to thank the organizers for inviting me here, and it's a great honor, of course, for me to give a talk at a conference dedicated to Professor Baxter. My talk will be on geometric aspects of integrable systems, on geometric interpretations. It's on discrete integrable systems, discrete surfaces, and it will focus on orthogonal ring patterns. First of all, oh God, I'm sorry. It's two. You probably see two slides, yeah, right?
Yes. I've never seen that before.
Let me change the mode. I apologize, yeah. Single page. And now, oh God, you. So, is it better now?
Yeah, it's better.
Okay.
So you need the full screen mode.
Well, I'm using a huge monitor, and then you see two pages. Let us. Is it okay this way?
Yeah, that's good.
Okay, good. So let me say a few words about geometry and the interrelation of geometry with integrable models of statistical mechanics. This is properties of geometric invariance of models. The most famous property is a conformality of models. Another one is this move to higher dimensions, which is famous. Baxter's Z invariance. This move of to higher dimensions was mentioned already by Volodya today. So this is Baxter's Z invariance, or there are many related things like spider move, multidimensional consistencies, and so on. And the pioneering paper on this is due to Rodney Baxter. Another thing is some of the model allow geometric interpretations in terms of discrete. There are numerous examples like circle patterns, and I remember how 10 years ago in the conference Baxter 2015, I was talking to Professor Baxter about invariance of circle patterns. Today, I'm glad that I can explain something new with much more involved model. Some models can be solved really using geometric methods. The corresponding states can be, for example, described as random surfaces quite geometrically. And a very famous example is the height function in the theory of diamond models. Okay, so I will talk on orthogonal ring patterns, but let me say a few words about orthogonal circle patterns. My talk will be essentially about geometry. There will be many pictures. There will be some equations, and I will focus on them as well, but let us enjoy pictures also. So here, when you are talking about circle patterns, I would like to mention two fundamental works. One of Fodor Schramm, who has described orthogonal patterns, orthogonal circle patterns with combinatorics of the square grid, and has found the integrability properties and has used these integrability properties for the investigation. So why are they interesting? Because it's known that they converge to conformal maps, and circle patterns were established as discrete complex analysis. There are famous results about discrete versions of Riemann mapping theorem due to Thurston, and also integrable equations appear here. So there are numerous papers about this, and this field is quite well established. I will just mention an integrable equation which describes orthogonal circle patterns. It's quite easy. You consider a circle, the combinatorics is a square grid combinatorics, and a circle with its four neighboring circles intersecting it orthogonally, like in this picture. And then the radii, R is the radius of the central circle, and R1 to R4 are the radii of neighboring circles. They satisfy an integrable equation. A Hirota equation written here, it's written in the complex form, but it's a formula for the central radii in terms of the boundary radii. So that's the story about circle patterns. Now, what I would like to talk about today are ring patterns, and this is a new notion. So this is a geometric generalization of circle patterns, and this geometric generalization is described by integrable systems, and this is an important integrable system. So what is a ring? A ring is simply a pair of concentric circles. So shown here in blue and in red, this is an inner and an outer circle with two radii, capital R and small r. We assume that the combinatorics is Z2, and then these circles are labeled by two indices. Then what does it mean that two neighboring rings intersect orthogonally? This means simply that their outer circle of one ring intersects the inner circle of a neighboring ring orthogonally. So you see this in the picture to the left. Yeah, so there are two intersection points, which actually there are four intersection points, but due to the symmetry, there are two different, where you assume this orthogonality condition. Then a consequence of this is that you have pictures of four neighboring rings coming to a point. And at this point, this is a picture in the middle. At this point, two inner rings touch and two outer rings touch of two pairs of the corresponding circles, as you see in the picture. Now let us look at immediate consequences of this. So you see two right-angled triangles here to the left, and then if you write down the Pythagorean law for these two triangles, then immediately you see that the differences of the squares of the corresponding radii of the outer and inner rings are constant for two neighboring rings, and therefore it's a global constant for the whole ring pattern. Then, therefore, of course, this equation can be resolved, and instead of two radii, you introduce so-called raw radii using this hyperbolic function uniformization. And the difference of the squares of the radii can be interpreted, of course, as the area. And the immediate consequence is that orthogonal rings have the same area for the whole pattern. Okay, so this is a typical picture which with the combinatorics of Z2, and then you see that there is some anisotropy in the picture. So for example, in this horizontal direction, we have inner circles touching at the corresponding points, and in the vertical direction, you see you have outer circles touching. And since generically these inner circles are smaller, then it brings you an anisotropy to the model. So it's not a conformal model. Okay, now let us look at equations. We have introduced already this raw radii, and then if you just consider a flower, like we have seen already in the Hirota case, then you go around the central circle, and write the formula for the corresponding angles. The sum is, of course, 2 pi. That's what we see here to the left of this equation. And this is a formula for the intersection, for the opening angles at the central ring. So this means that all these rho radii should satisfy the corresponding equation where the sum is taking over neighboring rings. So this is the equation for logarithmic radii of orthogonal circle patterns. This is not quite trivial claim. This means that this equation coincides with the corresponding equation for circle patterns. And it also depends only on the difference of the rows, and therefore there is a one parameter family of rings, of ring patterns, which can be easily obtained from one. Moreover, this equation turns out to be equivalent to the integrable here of the equation I have mentioned already. So therefore, it's not much new here. So comparing to the theory of circle patterns. On the other hand, I would like to mention that you can solve global problems with this, and this will be important in the future. For example, here you see a solution of a Neumann boundary problem. It follows from the fact that there is a variational description of circle patterns or the ring patterns, and therefore, just by minimizing the corresponding functionals, you can get such results. So now let us switch to the main topic of my talk. And this will be orthogonal ring patterns in a sphere and hyperbolic plane. So you see in examples of this to the left and to the right. So this is a round sphere with round circles, with round concentric circles. Same definition, almost the same picture. And this is a conformal model of a hyperbolic space where you also have pairs of concentric circles, and they are hyperbolically concentric. They are concentric in hyperbolic geometry, not in the Euclidean geometry, of course. So a great difference to the theory of circle patterns is that these models are not related by stereographic projections. So in the circle patterns case, the models are conformal, and therefore you can map one model to another, at least locally. Here it's not the case, because if you take two concentric circles and apply a stereographic projection from the sphere to the plane, then you will obtain, of course, two circles, but they will not be concentric anymore. And this implies that has a consequence that equations are essentially different from the Euclidean case. Yeah? There is again a relation to integrable systems and a relation to discrete surfaces. That's what I will try to explain. Let us look at the spherical case first. Yeah, so that's this case to the left. And what we do now, we write the spherical Pythagoras theorem. So look at this line, cos times cos. So R's now are the spherical radii, the radii of my circles in the spherical geometry. So they are measured in angles. So these small and capital R's are angles. And you have this equation, which is the spherical version of the Pythagoras theorem. And in the hyperbolic case, instead of trigonometric functions, you simply have hyperbolic functions and the same kind of description. Immediately from there, you obtain global constants. Namely, from the first line, you see that the quotient of cosines of capitalized and small r's are constant for all rings. And this is a global parameter of the model. The same is true in the hyperbolic case, where Q is the quotient of the corresponding cosh functions. Okay, so that's a very simple fact. Which is less trivial is that you can resolve these equations and uniformize the corresponding parameters, the corresponding functions in terms of elliptic functions. And this parameter q, which we obtain here geometrically, turns out to be just the modulus of an elliptic function. So in the circular case, we come to this parameterization. So this is the equation which we resolve. And then all variables are expressed in terms of Jacobi elliptic functions with this modulus q. Beta now plays the role of this raw radius, which we have seen in the Euclidean case. So I haven't mentioned this, but you should be able to consider here rings with positive and with negative orientations. And everything can be parameterized in terms of these elliptic functions, and depending on in which region of our torus beta lies, you have positive or negative orientation. Okay, now next step. We would like to derive now the equations for these betas we just have defined for our uniformized radii. And then again, the same story. You go around a ring, take the sum of the corresponding angles, and this sum is 2 pi, and then you can express this analytically in terms of this g function. So just a computation, quite similar to the Euclidean case. What is remarkable here is that these orthogonal ring patterns allow an interesting variational description with the functional, which is described here. It's a sum over all the edges. And where f is given explicitly in terms of these elliptic functions. And this is a sort of elliptic generalization of dilogarithm function. Because in the circular pattern case, these functions are given in terms of dilogarithms, and there is a geometric interpretation in terms of hyperbolic volumes of the corresponding polyhedra. So here, it's an elliptic generalization of this. So now, what is the circle pattern limit? Of course, we can let this parameter q go to 1, and then the area of our rings goes to 0. And then it turns out that ring patterns converge to circle patterns. And here you see 3 pictures showing this. Yeah. So to the left, q is almost 1, and then we go away from 1, deviate from it, and make rings thicker and thicker. Then applying implicit function theory, you can really prove this, the corresponding theorem that this deformation exists, and it's unique if you keep the boundary conditions. Okay, same story for hyperbolic ring patterns, similar uniformization with elliptic functions, but a different one, similar equation which describes us the radii. The only difference is this plus here instead of the minus, and the plus in the corresponding functional, but important changes. Yeah. So namely that in this case, because of this plus instead of minus, we have the convexity of the functional. So if you compute the Hessian of the functional, it's written here, then you see it's sum of non-negative terms, and it's never degenerate, so it's a convex functional. And what we are looking for a variational description. Yeah, so we are looking for critical points of this functional. And of course, if the functional is convex, then it's a pleasure to find these critical points. You just minimize this functional, and then you get uniqueness and existence results. And also, since everything is explicit, you can compute everything. Yeah. So there is this theorem that for any choice of the boundary radii or angles that correspond to Dirichlet or Neumann boundary conditions, there exists a unique orthogonal hyperbolic ring patterns. The basic tool here, there is some work here, but the basic tool is the convexity of the corresponding function. So smooth limit. So we have rings, and now the smooth limit is interesting because we would like to understand what kind of system we are investigating, what kind of system we are discretizing, whether this smooth limit exists at all. So you consider small rings. The size does matter here because you fix the curvature, you're on the unit sphere or in the unit disk when you're considering the hyperbolic plane. And then you pass to the limit q goes to 1. The rings are small, the area goes to 0, and these rings are smoothly varying in space. That's the way how you can come to the limit. So you can make this precise, introduce small parameter epsilon, which goes to 0, and describe explicitly what kind of behavior of these discrete variables is required. And then you see that in the limit, these discrete variables describe your solutions of the elliptic Sinch-Gordon equation written here with plus and with minus. So there are two versions. One is responsible for harmonic maps to the sphere, another one to the hyperbolic plane. And it can be interpreted as a discrete integrable system or sigma models, what we are doing now. So it's an integrable model. In the limit, you get the Sinch-Gordon equation in two versions, in the spherical and in the hyperbolic case. And these equations are very well known in the surface theory. So that's what I also would like to mention. Let us come to equations again. And that's this story about multidimensional consistency. The equation is integrable in the following sense. If you consider variables sitting at the vertices of squares, and they should satisfy the same equation on all faces, then the 3D consistency can be formulated in the following way. This is very much related to this Baxter-Z invariance. So you consider a cube, you consider 4 arbitrary fields at these black corners. Then you compute using this equation for 3 fields in the white vertices. And then there are 3 different answers for this white box vertex. And if they coincide, then it's an integrable system. So these equations were classified some time ago. And there is so-called Q4 equation, which is the master equation, and all others can be derived from this in the limit. It is parameterized in elliptic functions, and the geometric interpretation of this equation was a long-standing problem. Yeah, so we didn't know that. So if we will look at the corresponding equation describing spherical and hyperbolic orthogonal ring patterns, then the equation is written here, and the result is that it's a special case of this Q4 integral equation. So we are in the integrable setup. So this is an integrable theory. And now I hope I have 5 more minutes. Is it right?
Yes. Yes.
Okay, so let me conclude with relation of this to the surface theory. So here in the picture, you see an example of a surface with constant mean curvature. The equation describing this, the Gauss equation, the equation for the metric, is written here, where Q is a quadratic differential on the Riemann surface. So in the case when this quadratic differential is normalized to be 1, so for example, you're in a torus, then you are in the setup of the Sinch-Gordon equation. But the theory is developed also for the case when it's not normalized and when it's on the Riemann surface. So in this way, you can define n-noise, for example, surfaces with constant mean curvature shown here, periodic reflection surfaces. There is so-called DPW method based on Iwasawa loop group factorization to construct such surfaces. It works numerically quite well, but the proof of existence is problematic. So you see here a couple of surfaces which were obtained this way. It's also integrable theory, but completely different from the one I'm talking about. So now what is our setup? What is this path to discrete constant mean curvature surfaces? So circle patterns on the sphere are related to so-called Kobe polyhedra. They circumscribe a sphere, round sphere, in such a way that all edges are tangent to a sphere, not the faces, not the vertices in the sphere, but the edges are tangent to the sphere. And there are great theorems about this, about existence and uniqueness, such polyhedra. So, and then given such a polyhedron, so already a long time ago, we have described how from such a polyhedron one can construct a discrete minimal surface. So let me not go into details. The message is that now very similar construction exists in the case of constant mean curvature surfaces, where you simply should replace circles by rings. And this is a way how one can recover the geometry from the combinatorics of curvature line. So that's a new version of this Kobe polyhedron with two spheres, two concentric spheres. One half of the edges touch one sphere and another half another sphere, and they alternate. So to the left, you see such a two-sphere Kobe polyhedron. The corresponding ring patterns you see to the right. And let me show you the results which you obtain for surfaces. So in the middle, you see spherical ring patterns, orthogonal ring patterns. To the right, you see the corresponding discrete constant mean curvature surfaces. I haven't explained how to construct them, but there is an algorithmic way. Yeah, sure. If you have the data in the middle, you can simply construct these surfaces. And to the right, you see the corresponding smooth surfaces which were obtained by using other methods, other integrable methods, but completely smooth theory. You see that they are quite similar. Let me give you one more example of these geometric similarities. So from spherical ring patterns to constant mean curvature surfaces. And here you see three surfaces with constant mean curvature. The one in the middle has constant mean curvature 0. It's a minimal surface. Physically, it minimizes the area of the corresponding surface with fixed boundary conditions. Constant mean curvature surface minimizes the area for the case when you have a difference of pressures inside and outside. So you push some air inside the surface and it becomes more round comparing to the surface in the middle, and it looks like this. Yeah. So, but there is a unique surface, and that's the physical soap film, soap bubble model for constant mean curvature surfaces. So that's again minimal surfaces, constant mean curvature surfaces. This next question is, what is known about convergence? Convergence is known for minimal surfaces, for circle patterns, and the convergence is even with all the derivatives. So when we build the models of discrete and smooth, which we see here, then you see that they fit very good, and so therefore probably there is a C-infinity convergence. So I would like maybe to finish with this open question of C-infinity convergence. And that's, of course, also the story about the discrete Finch-Gordon equation and the continuous one, and the approximation of solutions satisfying some boundary conditions, which you see here. And but I think that these images, as I said, computed by quite different methods, are quite convincing that this discrete theory converges, and there are some preliminary results in this direction. So let me finish my talk with some recent papers which were published on this, and maybe with this image, which show us integrable geometry, integrable discretization, and also, as I said, in the circle pattern case, there is an interpretation of this in terms of models in statistical mechanics. I do believe that in the future, maybe in a couple of years, there will be similar interpretation for these constant mean curvature models and for ring patterns. Thank you very much.
I'd like to note that we have already quantized
Your U4 equation, so we do have already statistical mechanics formulation for these models.
Yeah, that's true. Yeah.
Any more questions? If not, let's start the speak again.